So the second axiom that we're looking at is the independence axiom. Preference relation on the space defined on the space of simple lotteries L satisfies the independence axiom if for all L, L prime, and L double prime, which are three lotteries in the space of simple lotteries, given a particular probability alpha, which is a number between 0 and 1, if we have L is preferred to L prime, then the independence axiom says that we can mix each of these lotteries with a third one, L double prime, such that the preference ordering does not change, right? So if we mix in L with a third lottery, L double prime, we get this mix, and that must be also preferred to a mix of L prime with L double prime with the same probability weightings. Now this assumption that we can mix two lotteries with a third one, and the preference ordering with the resulting compound lotteries will not change and is independent of the particular third lotteries being used, in our case L double prime. This assumption is actually not as innocuous as it seems. What is the justification for this result? Well, in essence, the justification is that outcomes that occur with the same probability under two alternatives should not affect your preferences over those two alternatives, so that this third lottery L double prime here does not affect the ranking between L and L prime. And one justification could be that L double prime is irrelevant here because the consumer will never consume jointly L and L double prime or L prime and L double prime, but only isolated in isolated occasions. So it's one or the other, one instead of the other, but not jointly. So there is an interesting implication of the independence axiom, which is that if we take 2 points on the simplex, consider two lotteries which are held indifferent, Li and Lj, for example, happen to be indifferent. If we connect them with a straight line, then all of these points on that straight line in between the two lotteries are also held to be indifferent. So the indifference surfaces are straight lines. Now this is not immediately obvious, but we can prove this result fairly easily as a direct application of the independence axiom. So we start with Li and Lj being indifferent, and we can now combine them with a third lottery. Let's pick Li as a third lottery. So the third lottery happens to be Li, and we add alpha Li to both sides. So what do we get? Okay. The left side is simply Li. The right side is unchanged. Okay. Now let's do this again. Same starting point, but now we add a third lottery Lj with a probability that we pick to be 1 less alpha. So we add this to both sides. Okay, the right side will simplify to Lj. And now, what do we have? All of this summarizes to Li indifferent to a linear combination of Li and Lj. And this is from this part here. And this linear combination of 1 less alpha Lj plus alpha Li, we identify here again, and that's indifferent to Lj. And we have proved our result, which is that if Li and Lj are indifferent, a linear combination of Li and Lj is also indifferent. So indifferent surfaces are straight lines.